So just a short announcement at the beginning. So about the final projects, we want you to work in teams of 3 persons or more, right? Or more. And so the first step is for you all to arrange into teams. So what we're going to do is later today, I'm going to post a Google survey on Piazza that you please all fill out, and it's going to ask you for the names of your group members and a tentative project title. That title can be totally changed later. Like if your group just should have some common discussion ground here. If you later on decide you want to use different data, you want to do everything differently, that's fine with us. It's just so that we know you formed your group and you have an idea what you would like to work on. And the deadline for this is going to be the 23rd of October. So you have a bit of time to like find the groups and discuss everything with your team partners.
Thanks. And one of the things we want to have an idea on is what the general topic is of what you're going to do, because that'll help us assign you TFs to help you decide if it's if the project that you're deciding on is good or not. So the whole point of of you turning in the project by the first part of the project is to make sure that you have a good one before you go and start working on it full on. Okay? All right, so another thing I wanted to announce is that if you just can't think of anything to work on, I have a list of ideas that you can ask me about, and I can give you some of the things I've thought could make good projects. I'm hoping that you all can find something interesting that you're interested in working on, but I do have a few things that I think are pretty interesting on their own, regardless of your general interest. Okay, so today we are covering Bayesian statistics. You're going to need this for the homework 4, which is coming up, was going to be announced on Tuesday, but I can tell you already it's mostly going to be predicting the midterm election. So what you're going to do in this homework is create confidence intervals and, as we'll explain today, posterior distributions and simulations for the election that's coming up in about 3 weeks. And the outcome of the election will be used to some degree in grading your homework. Okay, so today I'm going to explain some of the concepts that you need to do this, to be able to make statements like the probability of this candidate winning is such and such. How is it that those statements are made using data? So I forgot. But this is the results of homework 2. Again, pretty much everybody did really well, so I'm happy about that. See the distribution there, a lot of 10s and 9s. Okay, so here's just to get us started with Bayesian statistics. This is a very typical way in which we use Bayesian thinking is when we take a test for a disease. So here I'm telling you about a specific test. This is for cystic fibrosis. That is very accurate. So it's 99% accurate. And what I mean by that specifically, and now I'm going to start introducing some notation. So there you see the prob. Now we're talking about a probability. The probability of a positive test, if you have the disease, is 99%. And the probability of a negative test, given that you don't have the disease, is 99%. So it's a very, very accurate test. So here's a question to get you thinking about this. And again, this is something that you can use sometimes to make yourself not get too nervous after you test positive for something. So you can use this argument if you ever test positive for drug use or something like that. So if we select a random person and they test positive, what's the probability that they actually, ignore what it says, that they have the disease? All right, so that's the question that I'm asking you. So Now we're asking something different. Now we're asking, what's the probability that you have the disease given that you tested positive? So anybody have an intuition for what the answer to that question is? So if you have the disease, the probability that you test positive is 99. But now I'm asking you, what's the probability that if you tested positive, so you went to the doctor, they got the test, I guess you were very young, and you got a positive test, what's the probability that you have the disease? Anybody? I don't expect you to give me the right answer, but the ballpark. Who thinks it's 99%? Who think this 1 in 3,000? So ballpark. Anybody have a ballpark figure you want to throw out that you really feel is right? Nobody? No idea? Yeah. So you're saying it's going to be very small, much smaller than 99, right? That's the right intuition. So let's see. Let's work it out. So the Bayes rule tells us how to make this calculation exactly. So we have all the information we need to make this computation. So this is Bayes rule. It's super useful. You're going to use it often if you become a data scientist, and you're also going to use it in your daily life if you don't want to get too hysterical about some test, for example. So what it tells, there's a formula. So it says that if you want to know the probability of A given B, you're going to compute the probability of B given A times probability A divided by the probability. So I'm going to show this in a graphical form to help you understand why that is. So this is what we're asking now is probability of A given B, and we actually know all the elements on the right. It's pretty common that you'll know the elements on the right and you want to find out the one on the left. My left. So in the case of this disease, if we use this rule and we actually make the computations, right? So now I want to know the probability of the disease given that you tested positive. So the A and the B are the D and the plus now. You just apply Bayes' rule, and you get this formula. You get that it's the probability of positive given that you have the disease times the probability of disease divided by the probability that you tested positive. So we work it out. We stick on all the numbers. We get that it's 2%. So if you test positive for cystic fibrosis, if a random person tests positive for cystic fibrosis, it's only going to be a 2% chance of having the disease. So just so you can see this, I'm going to show you a simulation so you get a sense for why that is. The main reason is that it's so rare to have cystic fibrosis. It's 1 in 4,000. That when the test fails often enough when in a big population that you will get a large number of what are called false positives. That means you get a positive test when you actually don't have the disease. So I'm going to show you a little simulation that hopefully it will help you understand intuitively why this formula works. So what I'm showing in the simulation on top is the population. These are all the people, all the population that's going to be tested. And the little red points are people with disease. So I changed it a little bit so that it would fit on the screen, so it's not 1 in 4,000 anymore. What did I use? It's about 1 in 10. But it's still a small number. So there's 5%, 1 in 20. So we know that the probability in the population is about 5%. So there's 5% of those dots are red. So what we have then is every person is going to get tested. And here you're going to see in the simulation, you're going to see that this little dot here is going to show you an X whenever the test failed. So if the test fails, you call the wrong answer. You send someone red here, or you send someone gray over here, whenever the test fails. But the test fails very rarely. So we're going to go one by one, testing everybody. Every once in a while, we're going to make a mistake, and it'll go here if it's a gray, here if it's a red. So everybody gets tested. So as soon as you get tested, you get put in one of these two boxes. So at the end of the day, we're going to have this box here is going to have some reds and grays. This box here is going to have some reds and grays as well. So if we go back to the formula, what we want to know is what percent of reds in here, right? That's what we want to know. What is the probability that I'm a red given that I'm in this box, given that I tested positive? That's what we're going to do at the end. So we want to know what percent are here. So what percent are those? First of all, the denominator is this thing. That's as we expect, is how many, all the people that test positive are going to come in here. So that's the proportion of people who tested positive is going to be the number of people here divided by the number of people here. So that number, the number of little dots in this box, is the denominator. And the numerator is the people of it's the proportion of people who tested positive that do have the disease. And that's what this denominator is. All right, so it's the proportion of the reds that ended up in this box. And that tells us, so you divide the number of reds in this box by the total number of points in that box. And that's what this formula is. This is proportional to the number of reds in that box. And this is the proportion of numbers in that box. So here goes the simulation. You can see it. Every once in a while, you get an X. Most of the time that we get an X, we're testing a gray dot. So a gray dot is sent into this box. And you can see that this box actually has a lot of gray dots in it because 10% of the gray dots up there are coming over here. The opposite isn't true. There isn't too many false negatives. So very seldomly does someone get told they have the disease when they actually don't have it. But the opposite is quite high. So I'm using the different proportions that in the cystic fibrosis. But if you work this out, so this is the test that's going to be wrong 10% of the time. If you count the X's, it's about every 10 tests we see an X. You see the X, that's a mistake is the X. So about 10% of the time there's a mistake. So that's the probability of positive given that you don't have the disease, or the other side, the probability of calling when you don't. And then the probability of D is just the proportion of reds here. And as I said, I wrote it down here. The other probabilities that you're computing are going to be the proportion of reds in here, for example, is what we're interested in. So if you follow that along, you can see it. You'll convince yourself that there will be a lot of cases where you have gray dots in this box because, again, there's mostly gray dots in the population. So in the case of cystic fibrosis, the number of red points is tiny. In a box like this, there would only be a couple. But in the test is 99%, so about 1% of the grays would go in here, and that would still be a pretty big number compared to the reds. All right, so this is it's a simulation showing Bayes' rule. Okay, so now we're going to use it in practice, and we're going to go back to baseball. We're going to use the same ideas to make a decision about what to do with this player that is performing very, very well. So this is a real example from last year. So this is Jose Iglesias pictured here. He, in the month of April, was batting .450. That's 9 divided by 20 is 450. So what we're going to try to do here is predict his batting average in October. So this is April. They play throughout the summer, and we want to predict what his batting average is going to be on October. So when you see something like this, that is our estimate. And when this happens in real base, in actual, when this was happening, nobody was commenting it really in the sports news. And if we were to continue this pace, this would be quite a feat, because no one has done it since 1941. No one has batted above 400 since 1941. So that means that the number of hits divided by the number of bats hasn't passed 400 in almost 80 years now, 70 years. Okay, so the question is, so the question for me to you guys is, what would you have predicted? Some of you might have already know the answer because you can see it on ESPN's database. But what would you have predicted he would bat throughout the season? Okay, so that's the question. So anybody want to throw out a guess? We can take some without looking at ESPN. Anybody want to take a guess? Who thinks he's going to end up with 450? Anybody want to say a number? 220. Oh my God, that's very pessimistic. Who thinks he's going to have a 600? Why not? Why not 600? You're doing Bayes' theorem in your head. That's why. So those that follow baseball and hear me say 600, they just think that's ridiculous. But why? I mean, 450 is a small sample size, but he could have been unlucky, could have been lucky, it could have gone either way. Okay, so anybody else? We have a 220. What else? 250? 350. Okay, positive. Anybody else? So nobody's saying 450. Why not 450? Why not 450? Seriously, why not? Nobody wants to. Nobody is willing to go to the thing that the data is telling us we should do. Why is that? So what intuitively? Don't tell me mathematically. Intuitively, why don't you say 450? That's one way, right? You want to say something else? That's what I was going to say. Okay, but what about 380? Somebody said 220, right? How about 380? Does anybody believe 380? So let's do this more formally. But that's the intuition. No one has done it. Who's this guy? I mean, and what is that's only 20 data points, right? So it's very few information. So we're using information that is external to this particular data set. That's the data right now. That's all we have. So if you give this data set to someone who knows nothing about baseball and doesn't know anything else, they have no choice but to say, well, I got to go with 450. That's what the data says. But we have more. We have more information. For example, we have the distributions of batting averages for every player for the past 3 seasons. For example, we can go back, right? You did a homework. You can go as back as 1918 something. But I'm just looking at the recent season, and look how consistent that is. Every year, the average is about 275, and the standard deviation is about 2.7. No, 227. 0.027. So yeah. 27, right? So a typical player will be batting 275 plus or minus 40. 95% of players are within, what did I just say, 235 and 200 and 335, something like that, right? That's a typical player, and then there's some outliers, really bad hitters and very good hitters on the way at the top. But it's nice. It looks normal. Its average is at 275. So now we can use this. We can use Bayes' idea again. But it's a little bit more complicated because it's no longer just probabilities. Now we have a distribution. But that's what we're going to do. So here's the information we have. We know he batted 450. Another question is, other teams are impressed because he's so good. But we're the Red Sox and we use statistics. So the question is, should we trade him? given that other teams are so excited by him. So the first thing we're going to do is get an idea of what the standard error for his batting average is. So how can we compute that? So now we're thinking every time he comes to bat, it's just it's luck. There's a lot of luck involved. There's some true probability of getting a hit, which has to do with how good he is. That probability could be high or low. Right now, we're going to just assume it's 45%, but there is some luck. So it's either 0 or 1. So how can we compute a standard error if we think that way? What would the standard error be? How can we compute it? What do we use? What is this just like? Something we've done before. So think of what 450 is. What are you doing to get that number? You're adding either hit or not, 0 and 1, 20 times and divided by 20. So it's an average of zeros and ones, and that is, where have we seen that before? Averages of zeros and ones. Yeah? It's the binomial, it's a pole, it's like a pole. You can think of it as a binomial distribution. So we know what the standard error is, and now you can construct a confidence interval. If we just assume it's normal, we can just do it really quickly, and that's where we think he is. So we really don't have that much information. He could be terrible, he could be the most incredible player ever. 670, that's the confidence interval. Using this is what's called, I don't know if you guys have heard of the term frequentist. This is the frequentist confidence interval. So they were computing a Bayesian posterior distribution. The frequentist confidence interval just takes the data as it is and it does what we've been doing. So that's the information we have, and now the question is, should we trade him or not? So to answer that question, we want to get a better idea where he's going to. Can we get a better idea where he's going to be? Is he going to be on the 228 side or 672, or do we have no idea? Is he going to just keep about the same? And in which case we should not trade him because he's fantastic. Okay, so here is the equivalent of Bayes' theorem, but for distributions like the one we have. So for now, ignore the top one, the top formula, and just look at the bottom one. That is what we just did. We just said, if we know his real potential, theta, that's the proportion of times he will get a hit if we observe him forever. That's the true probability of getting a hit or not. We don't know it. But if we did know it, then the y that we observe, which is an average of zeros and ones, we know what that's going to be like. We know what the theta is we know what the average is going to be, and we know what the standard deviation is going to be. We just computed those two numbers. For our case, we don't know what theta is, but we know that sigma is about 0.11. Right? That's the variability that comes from luck. But now, we were doing the bottom one. We used the bottom one to get an idea of an interval that will be around theta 95% of the time. But now we're adding something new, and this is similar to the statement: 1 in 4,000 people have cystic fibrosis. It's an argument that goes to a higher level. Instead of at the individual, we're going to the higher level of a population. And in this case, what we're thinking of here is, in the first example, you say, take a random person. What's the chance that they have cystic fibrosis? It's 1 in 4,000. Now we're saying, take a random player. What do we expect their average to be? So that's what that distribution is like. We call it a prior. So what is mu and tau? We take a random player. What is the distribution of their batting average for a season, say? You should be able to answer that question with what you have seen. What are mu and tau? Yep. So we can go back if you want, and you can tell me what are mu and tau. Oh, damn it. What are mu and tau? 275 and 27. So that's mu and tau. So we know that mu, we know tau, we know sigma squared, we don't know theta, and we know what, and y we know as well. Y is the data that we saw. We saw y is what you end up seeing on a player. So let's run through this. And when you run simulations for the elections, you're going to do something like this. So you want to say I want to know what a random player is going to. I want to know the distribution of a random player at the end of April. So what do? I pick a random player, and now I know that once I have that player, I know their theta. I know what their real distribution is, theta, and now I can generate data for what happened in April, because I know that the distribution of y, given the theta I just picked, follows a normal distribution with a variability of 0.111. So now I generate that value. I could do that over and over and over and over and over again, and I will get the distribution of y, of any y, if I follow this exercise. All right. So now we can do this. So I just went through all this, so I won't go over it again. So here's filling it out. We have that the theta is normal with 275 and 27. And once we know theta, once we have picked a player and we have their true theta, then after April, after they have 20 at-bats, their standard deviation is 110. So now we're going to use these formulas to get to know what the distribution of theta given y is. Right, so we know we know this, but we don't care about that. What we want to know is what is theta? What is the value, the real value of this player, the real average for this player, which is represented with theta here. And we have seen y. So what we want to know is that all these ugly formulas, all they're saying, that top one, all it's saying is I want to know the distribution. So ignore don't be intimidated by the notation if it's the first time you see something like this. But all that is saying is I want to know the distribution of the real thetas if I condition on seeing y. So imagine you ran this experiment that I just described. You pick a player. You let them play 20 at-bats, you keep their y. You do this a million times. So now you have a bunch of y's that you've observed. You can condition on those y's, the ones that hit 450, for example, and then you can go back and see the distribution of all those players that ended up hitting 450 in April. What is their distribution of thetas? Now we're playing like we're creating all this ourselves, so we can see all this. In reality, we don't. But you could generate a simulation where you would see this. So that's what that is. You condition on all the people on all the experiments that in April ended up hitting 450, and you look at the distributions of the real thetas, the ones that I grabbed first from the first urn. All right. So let's go through over again. You have this urn of players, and the experiment goes like this. Pick one at random. Tony Gwynn. His real theta is 320. Play April. He hit 250. I was unlucky. Okay, throw him back. Grab another one. Alex Rodriguez. His real theta is 280. He went April. 100. Oh, wow. A-Rod did terrible in April. He doesn't like the cold. Throw him back. Grab another one. David Ortiz. He has a theta of about 290. Let him go in April. He hit 1,000. Wow, okay, keep him. So you keep doing this, and now you see these y's, and you keep all the experiments. You might pick, now you pick and you get Alex Rodriguez again. This time he hits 500. But his theta keeps being 280. That doesn't change. It was luck that got him, that made it change. So now you pick all the instances where you have a y of 450 and you look at the thetas for those players. So that's what that represents. And we can actually calculate that distribution without doing this crazy experiment I just described using Bayes' rule. Because what we have up there in the formula is the distribution of y given theta. We already know that. It's normal with a standard deviation of about 110. And we also have the distribution of theta. That's the distribution of players, all players. It's 270 plus or minus 27, and it's normal. The bottom one, the distribution of all possible outcomes, we can also compute because we know the top two. And that's a little bit more complicated. There's some calculus involved, but you can do that too. You can compute that mathematically. So we're not going to go over how to compute, how to derive these things, but you will be able to use these formula in homework 4 to generate poles. We're going to talk about that later. But these formulas are key for doing that. So once we know, because we can get f of theta given y, the distribution of the real batting average given the observed batting average, now we can maximize it. We know it's normal. We can, in this case, you can do the math and see it's normal. So the maximum is going to be the mean. So we want to know what the mean is of theta given y. And there's a nice little formula. It's very simple. That's what the mean is going to be. The mean of the distribution of the real batting averages given the observed is given by a weighted average B times the typical player plus 1 minus B times what you observed. So some of you already did that in your heads. Both of these people did that. 220 and 350. They didn't say y. Y was 450. They went down to mu. So they had in their head they had some mu that was smaller than 450, and they went down towards it. Right? So they downweighed the y and they weighted the mu. I think the person that said 220 had a very strong prior, and their b was practically 1. They ignored the 450 completely, so the b was 1, and they just used the mu. The 350, their b was a little bit not as big. They were using the 450. But now we're getting a mathematical motivation for what numbers we actually should use, because it just comes out of the math. And the v that we should use if we're going to use this Bayesian approach is the ratio of the variance that has to do with luck by the sum of the variance of luck and the variance of across players. And we're going to see that makes a lot of sense. Let's look at what happens. So let's say I have a case where I have observed a lot of data. So what happens to sigma squared when I observe a lot of data? This is the variability that has to do with luck. So if I observe 300 at-bats, now I have a binomial with 300, and I take the average. What is that? What happens to that sigma squared now? This is a similar question to what happens when you have a poll with a lot of people. What happens to the standard error? It gets really small. Right? So if I had a lot of data, if I have observed this person for, instead of 20, 300, the sigma gets really small, so B gets very close to 0. And that says, now B is close to 0, then what does the equation say? Look at the data. Forget your prior. It's been 300 at-bats. He's consistently done it. We're going to use the data, ignore the prior. Now let's flip it around. Let's say we haven't seen any data at all. Let's say it's the beginning of the season. What's sigma there at the beginning of the season? I mean, you can say it's infinity, right? We have nothing. It's as big as it can be. So when sigma is infinity, B is 1. Infinity divided by infinity is 1. Okay, so when B is 1, then we ignore the data, which in this extreme case doesn't even exist, and we're going to decide it's a random player. We've never seen him before. Mu is, I'm just going to guess his average is 270. See how it works? It's a nice little formula that balances between the typical player and the observed data. And we're going to go somewhere in between. Where we go in between has to do with how much we trust the data or our prior beliefs. That's the game that we play, and this math formula just tells us. We can compute it for Jose Iglesias, and we get that we're going to predict that for the rest of the year, he's going to bat 285. So it's kind of in between these two, this pessimist and the optimist. So we're giving a lot of weight. You see that 94.3. We're giving a lot of weight to ignoring the data. That's why the sportscasters don't get excited, because they, believe it or not, somehow in their heads they're doing this. It's kind of a very natural computation to do. I mean, I'm not saying they're actually using that exact formula, but they're using some kind of formula like this. So they don't get excited because they know this intuitively. They know it's not going to stick, and this is what is predicted. So the variance, now that, remember, we have y given theta. That's a distribution now. We can also compute, oh, there's a missing tau there. That's 1 divided by tau squared up there. This 1 is a mistake. Here is right. So this distribution has a variance as well. This is called the posterior distribution. The distribution of theta given y is posterior to seeing data. The prior is the distribution before seeing data. The posterior is the distribution after seeing data. So the SD for that is 0.26. It's a little bit smaller than the original one. No, sorry, it's a much smaller. And much smaller than the original one. And here's the final results using that information. So this over here. Here's the frequentist confidence interval. 450 plus or 220. That's just that's not useful, really. It's kind of too wide. And here's the empirical Bayes interval. And there's what actually happened. So this is real. This is the real data after April. In May, the Bayesians were he made them look bad, but then it kicked in the second half of the season. Okay? So notice that both answers are right. Do you see that? Both answers include what eventually happened. So they're both right. They both give you an answer that's correct. But which one's more useful here? I did this. Everybody see which one's more useful? Which one's more useful? Which of those two? If you own the team and they're asking you, and you're asking, should I trade this guy? They're offering me a bunch of money for him. Which of those two do you find more informative? The bottom one, right? Because it's telling you he's all right. He's not going to be that great. Go ahead and trade him, and that's what the Red Sox did. They traded him, and then they went on to win the World Series. All those statements are true. Okay, so that's how you use Bayes. That's how you use Bayes in baseball and in sports in general. When you see a team that's doing really well at the beginning, no one really gets too excited until they see more data. And in part it's because, or specifically with players, because they use empirical Bayes. They know the past. They know what's happened in the past. They know it's very rare for something like this to happen. So they don't pay too much attention to it until they get more data. Okay, so now let's move on to the elections. So this is going to be homework 4. So there's a map of the United States by states. The white states, there's no elections. Oh, sorry, I should say, for those who don't know, you should know this, I hope, that there's 100 senators in the United States. Every 6 years, they are up for election. About a third of them go up for elections every 6 years. So that ends up being every 2 years we have an election. And one's coming up in November 4, 7, what day is it? Anybody know? Nobody cares in Massachusetts because as you can see in that picture, it's as blue as can be. Ed Mackey is going to destroy whoever the Republican is. I don't even know. But that's not true in other states. So the point is that we currently have, so every 6 years, they're up, and it happens for a third. They stagger them. So every 2 years, some of them are up. So right now, 36 Senate seats are being contested. That's more than usual because there's these special elections because people retired or got a promotion. So there's a couple of special elections. So we currently have 55 Democrats. That includes 2 independents. They vote with the Democrats, so that's all that matters. And 45 Republicans. So right now, that's important politically because they can control certain things by having this majority. But 36 are being contested, which means that it can flip. So in this picture, I'm showing you in white are the states that have no election, and then in color are the ones, the 36 contests that are being held. 21 are held by Democrats and 15 by Republicans. So that means that the Democrats could be in trouble because more of their seats are up for grabs. So in the picture, we see states that are going to go Republican pretty much for sure in red. States that are going to go Democrat pretty much for sure in blue. Yellow ones are completely up in the air. And then the pink and the light blue are leaning either Republican in pink or Democrat in light blue. So what we're going to do in the homework is we want to go one by one, giving 2 things. We can give a confidence interval, but what we learned today is we can also give a posterior distribution of the difference, for example. So that's what we're going to learn to do today. We're going to see a little bit more on how it works. Okay, so let's look at some of these websites. So here's a website with, so the other thing I should mention is there's polls, as we know. You already did a homework where you looked at some of this data, and there's each individual poll is making a call at each state, but then we have these aggregators that, like us, we're all aggregators in this class. And here are some ones that are slightly more famous than us. Maybe they'll add us to this list soon. So those are the most famous aggregators. They're doing homework for every day. And you have New York Times, 538, Daily Kos, Huffington Post, the Princeton people, I don't know what PW is. Oops. Washington Post, Cook, Roth, and Sabato. So each one, you can see there, is making a prediction, and they have a percent. They have a percent there. Okay, so what does that percent mean? 99%. So let's look at an interesting one. North Carolina. No, the best one is Kansas. In Kansas, the Princeton people have the independent with a 72%. So what does that mean? Does that mean they think they're going to get 72% of the vote? So are you guys aware of what those numbers mean? Anybody want to tell me what it means? Say it again? The probability of winning. So we haven't done anything in this class until today that can let you do that. So we can compute a confidence interval for Kansas. So if you can take the data, you can compute a confidence interval, and what you're going to do is you're going to give me an interval. It's going to be like from 49 to 51 or something like that. You're going to say that the independent is going to get between 49 and 51% of the vote. And I'm going to say, wow, thank you for that incredibly valuable piece of information. It's not helping me, right? That's not letting me decide who's going to win. So that's what a confidence interval does. But there's no, you can't from there say the probability that this person is going to win is this or that. You can't. All you can say is the probability that this interval will fall on the truth is 95%. That's it. That's all you can do with that confidence interval. So this is all somewhat Bayesian. They're actually saying there's a posterior distribution of the difference, of the actual difference, and the probability that that difference is bigger than 0 is 72%, is what Sam Wong is saying in Kansas. Okay, so that's an important distinction to make, that you want to understand the difference between. Again, one, in the confidence intervals, we assume there's a truth that's going to be revealed in the election, and we're just throwing intervals at it. And we're throwing intervals that are random, but 95% of the time will contain that truth. They will fall on the truth. But the interval is what moves. This seems to imply that truth moves. It's random. Right? There's the probability of winning. It's not saying the probability that I'm going to get it right. They're saying the probability that this person's going to win is this much. So they are thinking it's a random variable. Okay, so before we continue, one thing I want to point out is I'm very disappointed, but it seems like Sam Wong has now accepted that Knight Silver is right, because look at their two, they kind of agree pretty much completely. So I'm looking at the Fox column, the second one, and the Princeton symbol column. You see how they're almost identical now? You go one by one, there's no debate anymore. So the only things that look interesting now are Kansas, like that. Well, I guess that's interesting, where you have some people saying it's going to be Republican, half and half, and some saying more optimistic. Oh, look, this one and that one is quite different. And then we have some other interesting ones. This one's interesting too. These are pretty sure that the Democrats are winning North Carolina, but Huffington Post isn't so sure. And there's one more that's interesting. I can't remember now. Oh, well, I guess it's Iowa is a little bit interesting, 87. There's a few. Okay, so one question about this. Which are the bold pollsters here? Who are the bold ones? Look at the figure and tell me. Who's the boldest of them all? Washington Post. Everybody see that? They're sure about everything except Kansas. Who's the least bold? Who's the wishy-washy of them all? Huffington Post. What a surprise. Just kidding. I don't know what that means. All right, Washington Post are like, I don't know. Yeah, they're like, yeah, Delaware's Democrat. Okay, so look at
even New Jersey, they have kind of light blue.
Okay, so the Washington Post is not very confident on. Well, that's not what I should say. They're not that confident about the results as the Washington Post. So where does this come from? How are these things so different? Which of these two are right? That's what you're going to have to do in your homework. You're going to do, and you're going to be put up there in some, and you can kind of agree with some and not others. Okay. Oh, I have to go back. Sorry. No. Okay. All right. So I don't have to see that. So here's a nice little figure that Nate Silver makes. So he has, again, he says chance, 90% chance. Oh no, he's falling on this range. So when you read the Nate Silver stuff, it's not clear what a model is and what he thinks is random or not, but he does talk about the chance of winning. Oh, there it is. So he has a chance of winning up on the right. And so he had these little figures showing you how confident he is. And then the other thing he does, which is something we want to do for sure, is get down to what matters. Who cares about the specifics? Well, we do care about the specifics, but more than anything, we care about who's going to control the Senate. So here, this is the most intriguing figure, I think. Here is, and all of them do make a figure like this. So what is being shown here is, for Nate Silver's group, is giving you for the number of Republicans, he's giving you a probability that that's going to happen. So they think that there is a 1% chance, there's about a 2% chance that the Democrats will continue to hold 55 or more. You see it here? 2%. They're not looking good. This plus this plus this is about 2%. That's 45 for the Republicans. That's where we are now. And then there's a big cloud around 52, 51. There's a kind of two. I don't know if that's really two modal, but that's what they think. They think it's going to be somewhere here. But one of the things that is interesting about this is that if you look at, I don't know what that is. If you look at the Washington, which was the one that was very bold, the Washington Post, how is their little diagram going to look? How is their histogram going to be different than this one? It's going to be peakier. It's not going to be as fat. So here's here's an interesting thing about all this, and this is part of what was part of the big debate in 2012 and 2008, is that if the Democrats get 53, that if the Republicans only get 47, you can't really say that Nate Silver was wrong, even though he's predicting 52 Republicans. 47, it's in there. It's not that unlikely. So he's actually conceding that he really doesn't know exactly what's going to happen. There's a whole range of things that can happen, and there's a distribution. So if we really wanted to test his ability to predict probabilities well, what we would have to do is wait 20 years or 25, well, 20 years times 4, 80 years, or maybe just every 2. Okay, so we can do it every 2 years. We wait 40 years, and now we have Nate Silver's distribution and what actually happened. Right, and we can see if at least on average, his distributions are really what was going on. Okay, so now let's go back to the data that we have at hand and see where things are interesting. So there you have these. This is what what the guy from Princeton, Sam Wang, I think is his name, what he's kind of doing, I think, from what I can read, is he's taking the polls for each state, and he's computing a confidence interval based on aggregating all the polls. So he might do some weighing, but what I make is it looks a lot like what he has. So what does he have? So in Kansas, he has 20 polls. He takes the average, that's the little point. He computes the standard deviation, divides by the square root of 20, multiplies by 2, adds to both sides, and that's his confidence interval. So these are confidence intervals, just straight averaging of polls. So when you look at this, you can see that if you use this approach, you're going to be much more confident about what's going to happen than, say, 538. You see that? You see how there's only like 1, 2, 3, 4, 5. There's only 5 or 4 states where the confidence interval includes both positive and negative numbers. So even North Carolina, which is supposed to be contested, they have it. They're pretty sure that the Democrats are winning, and they're pretty sure that the Kansas is an outlier, but they're pretty sure that, for example, the Republicans are going to win Kentucky. New Hampshire is another interesting one. New Hampshire is, look at how sure they are about New Hampshire. Ooh, that's not right. So New Hampshire, you can make a 99.99 confidence interval and it still wouldn't include 0. You can make that 3 times as big. So what's the difference? And how do we actually get probabilities? So here's one thing that we didn't show. These are the whole data, not just the points. And now let's look at this more closely. So here's Kansas. Kansas is the hardest one. Those are the probabilities of winning given by the different pollsters: 60, 56, 72. And They're all over the place. It's basically a tie. I think this one's very hard to predict. There's a plot that makes you think maybe the Republicans have the lead. Some of that information comes from a poll that you don't actually see it. It's way out there. If you include it in there, in the average, I don't think you really should. It makes you think that the Democrats have maybe a little bit of a chance. I don't know. It's hard to tell. This thing goes like this, maybe, right? Is there a trend going up and down? I don't know. Maybe. Right? So it's trending towards the Republicans. Oh, yeah, and all these plots, Republicans, which are the favorites, minus Democrats, are the differences. And then here's New Hampshire. There you can see the Democrats were winning, but now look at the trend. It's moving up. And then North Carolina. So North Carolina has some variability. There's one that's 96% sure that the Democrats are winning, while others are only at 60. So what explains that difference? So here's the data for North Carolina. Right, so what do we do? So how do we create this probability of winning or not? So here's what they do, something like this. So if you look at North Carolina, and you just use confidence intervals, the first one is if you use all the data, then you get from -4 to 2, so that's pretty much calling it for the Democrats. That's using all of it, but you really shouldn't be using that. Those are all the same pollster, that's what the color is. That happened a long time ago. If you come closer, then this is the confidence interval that you get. It's still pretty much calling it for the Democrats. So what you can do, and what Nate Silver kind of does, it's not clear what exactly he does, but what he seems to be getting at is he wants to construct theta given y. So he wants to know the posterior distribution of theta given y for each state. So the hard part here is the prior. How do they get these priors? That's hard. And then the other hard thing that they do is the standard error. Here I'm using 0.5. That's what you get just from taking the data. Is that really 0.5 or is it a little bit bigger? How can it be a little bit bigger than what you're getting? Well, we're going to talk about some of those things. So what they have to do first is figure out some kind of, if we were going to imitate what they do using Bayesian statistics, the hardest part is going to be figuring out a prior, and it might have several levels. So where could we get the priors? And here's what they do in these aggregators. One thing they do is they use the incumbent information. So if you didn't have any polls, what would you do? That's what your prior is. How would you say what's the probability of the Republican winning? So one thing to do is get information about incumbents. You might just break it down to incumbent or non, but the more times you've won, the higher your probabilities get. So one thing we can do is we can go back to 2010, and we can forget the polls data, just look at the outcomes and see what the distribution of differences were for the incumbents. I think it's going to be a little bit higher than 0. So that's one thing you can do. Another thing you can do, and now this is going to get a little bit more complicated, but another thing you can do is if you can see how the national field, there's a poll that keeps track of that. It's just you ask people, you take a random sample of people and you ask them Republicans or Democrats. That's it. They don't ask them about a specific race. And that you can also use to shift your opinion on who's going to win, knowing nothing else, knowing nothing about polls. And then with that information, you can figure out, if I knew nothing, if I had no polls, what would my prior distribution be of of the difference that I'm going to observe. Right? So now you stick that prior, and now you say, okay, given that I have this data, and I have all these poles, so I know what the standard deviation is from knowing that I have all these poles. So I know what y given theta is, and I can do all these computations that I did for baseball to get a posterior distribution as well. Okay, so the other thing that you're going to be able to do, so I'm kind of walking you through the things you're going to want to do for your homework, is if we want to recreate Nate Silver's distribution of how many times this happens and that happens. So for that, what we want again is the posteriors. What's the distribution of the difference, of the observed difference given to data? And once we have that, we can generate elections. So we'll have that for every state. Right? So we have this model that generates that creates a distribution for each one, and you can do it 10,000 times, generate election days, and in each one you'll sum up who won, Republican or Democrat, and you get a number for each one of these simulations, and you can make these distributions. Now if you want to compete with the real players, there's a lot of little things you're going to need to do to get it as good as what they get. One of them is that you can't assume that the polls, that if you're generating data for each election, you can't just assume they're independent. You can't just assume that each state generates an independent election, because you do know you can test it with data, and you can see it in previous years. You can see that there's movement that affects all of them. So in your simulation, you're going to have some level in this model where every state gets added this little bias, and that affects everybody the same way. And that'll make your distribution wider if there's correlation. Is that true? I think so. Your eventual distribution. Okay? So those are the kinds of things that you want to be doing. Again, you want to be able to compute the posterior distribution of the election day theta given the data that you've seen. So we're going to of course walk you through in the homework, but that's just to get you thinking about the general idea. And one thing that's, again, is going to help a lot is going back to previous years. Yeah, so there's another thing I want to mention before I stop is that you have, if you want a model that's realistic, that it's not too overconfident, I think you should add a bias of the polls. So all the polls might be a little bit biased one way or another, and we don't know what that is. But it is something that you could consider as random. And I have a little bit of data to support that, of the difference between the polls and the election year. You go year by year. You can see how that there was a little bit of a bias. And you can include that in a model as a random variable, again, through the prior, that generates extra variability. So you think you have it all right, but then you have to add a little bit of a mistake at the very end that says, everybody was off by like 1 point or negative 1 point. So every time you generate a distribution, that thing can shift, and that's also going to make your distribution wider. All right, but that's a general idea of how you create these things and the way you think about the model for the data in a way that you can actually make the statement, the probability of this or that is 60%, 20%, or 50%. Okay? I'm going to stop there and take questions. If anybody has questions. All right.